Welcome to the deep dive. Ready to jump into some machine learning? We're looking at ARC's fifth papers from February 1st, 2025.
Fresh research. A glimpse into the future of AI.
Absolutely. First up, heterogeneous multiplayer multi-armed bandits, robust to adversarial attacks. Intense, right?
Think of it like a game. Friends choosing resources, but if they pick the same one, nobody wins.
Okay, got it.
Now, throw in some adversaries messing with those resources, forcing the friends to adapt.
So that's where the multi-armed bandit part comes in.
Exactly. Like pulling a slot machine lever, you don't know the outcome until you try. These algorithms learn which levers to pull to win, even with adversaries around.
And they do this with minimal communication.
Just a single bit for a short time. The researchers made a policy for near-optimal decisions despite limited communication and adversaries.
So more resilient AI in unpredictable situations. Fascinating. This next one seems helpful for handling tons of data. What do you think?
NP. Practical enhancement of knockoff with overparameterization for variable selection is all about figuring out which variables matter when building a model, especially with huge data sets.
Yeah, picking the right variables is key in so many fields.
NP builds on the knockoff filter. Imagine finding real diamonds among fakes. It creates copies of each variable and uses a model to see which originals stand out.
Clever. So we can build more accurate models, especially in areas like genetics where the right variables are critical.
That's the goal.
Huge potential. Okay, U aggregation, unsupervised aggregation of multiple learning algorithms. Sounds practical, right?
Very. Imagine having a toolbox of AI models, each with its own strengths. How do you pick the best one for a new job, especially without labeled data to test them?
A common problem.
U aggregation combines predictions from multiple models for a better, more robust result, even without labeled data.
Like getting multiple opinions and combining them.
Exactly. It even considers variations in model quality. Some might be unreliable or even adversarial.
Wow, it can tell good advice from bad. Any real-world examples?
Genetic risk prediction. It combines models for more accurate and reliable risk assessments.
Like a team of doctors for a better diagnosis. Data privacy is a big concern these days. How does this next paper address that?
Optimal survey design for private mean estimation tackles collecting survey data while protecting privacy.
Sensitive questions without revealing identities. Tricky.
It uses differential privacy, ensuring individual data points can't be traced back from the results.
Like anonymizing data while still getting insights?
The breakthrough. A new survey design method balancing privacy and accuracy, so more reliable results while respecting privacy.
Amazing. This next one focuses on neural networks, specifically random feature neural networks, or RFNNs. What makes them special?
They're fast and efficient, but often lack the depth of complex networks. This paper bridges that gap.
Getting the best of both worlds.
Right. The new method, RFR-Boost, uses boosting, combining multiple simple models into a powerful one, like a team of experts.
Teamwork. Did they test this?
On 91 datasets. RFR-Boost consistently outperformed traditional RFNNs and even complex, deep networks.
Wow. So faster, more efficient, and potentially more accurate AI. Where could this be applied?
Think real-time decision-making, like self-driving cars or high-frequency trading where speed is key.
Giving those systems a boost. Now, unfaithful probability distributions in binary triple of causality directed a cyclic graph, challenging assumptions.
It reminds us about correlation versus causation. Just because people eat more ice cream in summer and get more sunburn.
Doesn't mean one causes the other.
Exactly. Hidden factors or complex interactions might be at play.
So don't jump to conclusions.
They show that even simple scenarios can lead to wrong conclusions about cause and effect if you only rely on correlations.
A crucial reminder as we use data for decision-making. Contextual online decision-making with infinite dimensional functional regression sounds intense.
Imagine navigating a maze with shifting walls, making decisions at each step based on what you've seen and where you want to go.
Challenging. How does the paper approach this?
Using functional regression. Instead of individual data points, it considers the data's overall shape and behavior over time.
The whole journey, not just individual steps.
And it handles incredibly complex situations where the influencing factors are practically infinite.
Infinite dimensions. Mind-boggling.
They created a framework that learns the probability distribution of possible outcomes, like a crystal ball showing a range of possibilities.
So a probabilistic map of the maze. What are some real-world uses?
A financial trading system adapting to market fluctuations, or a personalized recommendation system suggesting things in real time based on your changing preferences.
AI that anticipates and adapts to change. This next one is about particle filtering. Beyond prior limits, addressing distribution misalignment in particle filtering.
It's like tracking a moving target in a crowd with noisy sensor readings. You're trying to estimate the target's location over time.
Tricky with all the noise. What's the focus of this paper?
What happens when your initial assumptions about the target's location are wrong? Distribution misalignment.
Starting the search in the wrong place, throwing off the whole process.
Right. They introduced diffusion-enhanced particle filtering, giving the system the ability to explore beyond initial assumptions.
Wider search range.
It uses exploratory particles to venture beyond the initial area, finding the target even outside the expected zone.
A backup plan for wrong assumptions. Important for robotics and navigation, where accurate tracking is essential.
Absolutely. This next one looks at shallow neural networks trained on massive data, almost memorizing it. Optimal generalization and learning transition in extensive width, shallow neural networks near interpolation.
Pushing them to their limits, what did they find?
A phase transition, like water turning to ice. As the data increases, the network transforms.
So it's a similar transformation.
They found two phases. A universal phase where performance is consistent regardless of setup, and a specialization phase where the network fine-tunes and aligns with specific data patterns.
Learning general rules and then specializing.
And this transition happens abruptly as data increases.
Like flipping a switch. What implications does this have for building and training networks?
Understanding these transitions could be crucial for optimizing performance. Predicting the specialization phase could allow us to tailor training for maximum accuracy.
A roadmap for training networks to reach their full potential. Next up, rewriting the rules of deep ensembles. Deep ensembles secretly perform empirical Bayes.
Deep ensembles improve accuracy and robustness by training multiple networks and combining their predictions, like getting multiple expert opinions.
Wisdom of the crowd. What's the secret they uncovered?
They challenged the idea that deep ensembles are purely empirical, showing they actually perform Bayesian inference, a statistical framework for updating beliefs based on data.
So, a method to the madness.
It provides a theoretical explanation for their effectiveness and could lead to better ways to design and train them.
They're secretly following statistical rules. This next one combines machine learning with evolutionary biology. Interesting.
It's Bayesian phylogenetics. Imagine figuring out how different species are related, creating a family tree of evolution.
Phylogenetics can get complex, especially with many species.
Traditional methods struggle with the number of possibilities. This paper uses algorithms in hyperbolic space, a framework capturing the branching nature of evolution.
A map designed for navigating relationships between species.
Hyperbolic space handles vast possibilities more efficiently. These algorithms are faster and more scalable for large data sets.
A big win for evolutionary biologists. This next one tackles pricing and resource allocation, a common business problem.
Dynamic pricing and resource allocation with online learning is about setting prices and allocating resources when demand fluctuates, like managing a restaurant with unpredictable customer flow.
Finding the balance between supply and demand.
They developed an algorithm that uses online learning, adapting to changes in real time by learning from customer behavior and adjusting prices and resource allocation.
Like a dynamic pricing system adjusting to demand.
Achieving near optimal performance over time, almost as good as an all-knowing oracle.
A crystal ball for customer predictions and pricing. This could change things for businesses in dynamic markets. Okay, on to noisy labels. It's a data problem we often encounter.
Noise-adaptive conformal classification with marginal coverage focuses on conformal inference to quantify uncertainty in models.
Being honest about what the model doesn't know.
They developed a method handling noisy or unreliable labels, like a spell checker figuring out what you meant despite typos.
Love the analogy.
So, building more trustworthy and reliable models, even with messy data.
A big step towards robust AI for real-world data. This one uses machine learning for a specific application, estimating myelin water fraction in the brain. What exactly is myelin?
Myelin is a fatty substance coating nerve fibers in the brain, like insulation on electrical wires, allowing signals to travel efficiently. This research uses deep learning to estimate the water trapped within myelin, a key indicator of brain health.
AI analyzing brain scans for a better understanding of myelin.
They use input layer regularization, filtering data before it enters the neural network.
Pre-processing for easier learning.
Leads to more accurate estimations of myelin water fraction, with implications for diagnosing and treating neurological disorders.
AI creating powerful tools for medical diagnosis. This next one seems to be about hidden patterns in complex systems.
Fractal analysis for finance and economics dives into studying systems with self-similarity at different scales. Think of a coastline. Its rough shape looks similar from afar and up close.
Patterns repeating at different magnifications. How does this apply to finance?
Financial markets often display fractal-like behavior. This paper has a new algorithm for estimating the Hurst distribution, which measures the long-term memory of a time series.
How much the past influences the future.
Right. They combine spectral clustering and wavelet analysis for an algorithm handling many variables.
Breaking down a complex system to find recurring patterns.
Exactly. This could help identify hidden dependencies and long-term trends for better risk management and economic forecasts.
AI uncovering hidden order in seemingly chaotic systems.
Finding the signal within the noise, extracting meaningful information from the data.
Okay, this next one is Deep FRC, an end-to-end deep learning model for functional registration and classification. What's functional data?
Think brain activity, stock prices over time, or weather patterns. Data varying over a continuous domain like time or space.
Data that tells a story, like a timeline.
Functional registration is like syncing videos of the same event from different angles, aligning them in time to compare and see the bigger picture.
Aligning timelines for data analysis.
Deep FRC does both registration and classification, an editor synchronizing videos and giving you the key takeaways.
Impressive. Does it outperform existing methods?
More accurate and efficient, especially for high-dimensional data.
What are the potential real-world impacts?
Revolutionizing fields like medical imaging, speech recognition, and even gesture recognition.
Pushing boundaries in data analysis, making complex tasks simpler. Now we have estimating multi-chirp parameters using curvature-guided Langevin Monte Carlo, right out of sci-fi. What are chirps and why are they important?
Chirps are signals changing frequency over time, like bird songs or radar signals. This research extracts information from these signals.
Decoding those complex signals.
They use a Langevin Monte Carlo algorithm. Imagine finding the highest peak in a mountain range. The algorithm is a hiker exploring the terrain, using slopes and curves to find the optimal path to the summit.
So the algorithm has a map and compass for efficient navigation.
And it's robust, even with noisy or overlapping signals.
Real-world applications.
Audio processing. Imagine speech recognition in noisy environments or music software identifying different instruments.
Making sense of sound more sophisticatedly? Amazing. Decentralized, projection-free, online, upper linearizable optimization with applications to DR submodular optimization. Decentralized optimization.
A network of computers, each with local data, working together to solve a global problem.
A team of computers with a common goal.
This research introduces a framework for efficient decentralized optimization, distributing computation across the network. Each device contributes to the solution without needing all the data in one place.
A distributed brain.
And it applies to DR submodular optimization with applications in resource allocation and social network analysis.
Changing how we approach large-scale problems, especially where privacy and data security matter. Now let's look at PDE-DKL. PDE-constrained deep kernel learning and high dimensionality, which tackles partial differential equations, or PDEs.
PDEs are the language of physics, describing how things change over time and space.
The laws of nature written mathematically. But they can be tough to solve, right?
Especially in high-dimensional problems with limited data. This paper combines deep learning with kernel methods.
Two powerful tools for a tough problem.
This hybrid approach, PDE-DKL, uses a neural network to simplify the problem, then a Gaussian process to solve it while respecting the PDE's physics.
A rough outline filled in with precision.
Exactly. This could impact computational fluid dynamics, material science, and drug discovery, where solving PDEs efficiently is key.
AI pushing the boundaries of scientific computing. Now this next one dives into a mathematical concept.
Formal proofs for theorems related to the radon-Nikodym derivative delves into measure theory, measuring the size of sets. They provide formal proofs for theorems related to the radon-Nikodym derivative.
Measure theory is a bit beyond me. Can you simplify the radon-Nikodym derivative?
Imagine two ways of measuring object size. The derivative tells you how one measure changes compared to the other.
Like converting between measurement systems.
This has implications for probability theory, statistics, and machine learning.
Strengthening the foundation for future development.
Exactly. This next one is about energy-based models, or EBMs.
Okay, tell me more.
They're like landscape architects, creating a virtual landscape where low energy areas mean high probability and high energy means low probability.
A topographical map, peaks for unlikely events, valleys for likely events.
Training EBMs is difficult because of the partition function, a sum over all possible data points.
Calculating the area of a vast landscape. That sounds hard.
This paper uses two neural networks, one for the energy function, the other to approximate the partition function.
One scarps the landscape, the other measures its size.
This could lead to more powerful EBMs for image generation, text generation, and drug discovery.
A boost for generative models to create realistic and diverse data. Loss functions are next, a key part of measuring a model's performance.
They tell the algorithm what to optimize, what it should achieve.
It needs a clear goal.
This paper provides a framework for constructing loss functions based on f-divergences. Imagine measuring how different two groups' preferences are. F-divergence does that for probability distributions.
Measuring the dissimilarity of datasets.
This creates a new family of loss functions with different properties, some more robust to outliers or noise.
Giving the algorithm a nuanced way to evaluate itself, less affected by bad data.
And they developed efficient algorithms to optimize these functions, making them practical.
More accurate, robust, and efficient models across machine learning. Missing data is up next.
Imagine a survey where respondents don't answer all the questions. Missing data can bias results.
Not getting the full picture.
Prediction-powered inference uses machine learning to predict missing values.
Filling in the gaps with AI.
Their new predict-then-debias estimator handles non-uniform sampling, where data isn't collected randomly, a common real-world problem.
An AI assistant filling in gaps and correcting data collection biases.
Exactly. Impactful in social science, economics, and healthcare, where missing data is prevalent.
Enhancing statistical inference for more accurate analyses. Now, how about estimating property values with AI?
This research improves automated valuation models, algorithms using data to estimate a property's worth.
Like estimates, but better.
Quantifying the uncertainty in predictions is a challenge. This paper introduces spatially weighted conformal prediction, considering the influence of nearby properties.
So a house is worth more if surrounded by valuable houses.
Incorporating spatial information creates more accurate confidence intervals for value estimates.
More transparency and confidence in valuations. This next one delves into the theoretical side, combining deep learning with Sobolev spaces.
It's about nonparametric regression, estimating a function relating input and output variables without assuming its shape.
Finding the best fit without assuming it's a straight line or parabola.
They developed SDORE, a semi-supervised deep Sobolev regressor, a neural network incorporating Sobolev space properties.
A network designed for this type of regression.
It also uses semi-supervised learning, leveraging both labeled and unlabeled data.
Learning from examples with and without answers.
This allows SDORE to achieve impressive results, even with limited labeled data.
Impacting image processing, signal processing, and finance, where estimating complex functions is crucial. This next one is about the computational complexity of the Gromov-Wasserstein distance.
It's a universal measuring tape for comparing different objects, even in different spaces.
Saying how similar things are, even if they're not directly comparable.
They proved calculating this distance is NP-hard, meaning no efficient algorithm exists to solve it for all inputs.
A really tough problem.
It highlights the computational challenges, encouraging exploration of alternative approaches.
Even powerful computers have limits.
It emphasizes algorithmic innovation and understanding computational complexity. This paper focuses on transfer learning for lasso regression.
Okay, tell me more about that.
Lasso regression, or one-regularized regression, is like a detective finding culprits, figuring out which variables are responsible for an outcome.
Identifying key players in a complex system.
This research is about transferring knowledge from related datasets to improve lasso regression on a new dataset.
Using past experience for better future decisions.
They used sharp asymptotic analysis looking at the big picture trends to see how the algorithm behaves with large amounts of data.
Understanding long-term behavior.
They found that new transfer is much more important than way transfer.
The most valuable knowledge to transfer.
Making transfer learning more practical, focusing on the most important aspects.
Streamlining the learning process. Now let's hear about prospective learning, a new paradigm for prediction.
Traditional machine learning assumes a static world, that patterns from data will always hold true.
But the world constantly changes.
Prospective learning recognizes this dynamic nature, aiming for algorithms adapting to change.
Anticipating the future. not just memorizing the past.
They developed prospective ERM for prospective empirical risk minimization.
How is that different from traditional ERM?
Traditional ERM finds the best fit for existing data. Prospective ERM minimizes risk on future data, considering the evolving world. It equips machines with the ability to anticipate the unexpected and adapt.
Amazing. What about this paper on universal rates in empirical risk minimization? Universal rates of empirical risk minimization.
Empirical risk minimization is the core of many machine learning algorithms, finding the best-fitting model for observed data, minimizing errors on the training set.
Building a model for accurate predictions on new data.
These universal rates define the speed limit of learning, how fast an algorithm can converge to the optimal solution as data increases.
Understanding the limits of machine learning speed.
There are only 4 universal rates for ERM learners, 4 different speeds of improvement regardless of algorithm sophistication. Some problems are inherently easier to learn.
Like lanes on a highway, some algorithms stuck in the slow lane.
Exactly. And they characterized which problems fall into each category, a roadmap of the learning landscape.
So we understand what's achievable with different algorithms. Next up, omniprediction.
Omniprediction goes beyond traditional prediction, creating a single model for accurate predictions across a wide range of loss functions, even those not considered during training.
A versatile prediction model, adapting to different accuracy measures.
They developed algorithms for near-optimal omniprediction in online and offline settings, handling both streaming and static data.
Covering all the bases. Where could this be used?
Think of a recommendation system adapting to evolving user preferences, or a financial algorithm adjusting to different risk tolerances.
Flexible and adaptable AI. This next one tackles dynamic treatment effects, crucial in healthcare and economics.
Imagine evaluating a new drug's effectiveness, but the effects change over time or depend on previous treatments. Those are dynamic treatment effects.
The impact varies based on the individual and timing.
This paper has a new estimator for these dynamic effects, handling high-dimensional data and potential model misspecification.
Like using the wrong tool for the job, leading to inaccurate results. How does their estimator handle this?
The sequential model doubly robust estimator is robust to certain types of misspecification, a safety net to prevent the analysis from going off track due to inaccurate assumptions.
A game changer for evaluating interventions in healthcare, education, and policy. What about active learning in contextual linear optimization?
Active learning is a student asking the teacher for clarification on key concepts.
Learning efficiently by focusing on the most informative data.
This new active learning algorithm uses a margin-based approach, finding data points on the boundary between decisions.
The tipping points influencing the decision.
Their algorithm significantly reduces the labeled data needed for good performance.
A win for personalized pricing, route optimization, clinical trial design, all sorts of things. What about virtual humans?
This virtual human generative model uses a masked modeling approach, like taking a photo and letting the model fill in personality, lifestyle, even health conditions.
A complete digital twin from partial information.
Trained on real human data, the model learns relationships between attributes, generating virtual humans with diverse characteristics.
Possibilities for gaming, VR, healthcare training, even research. Personalized avatars, medical simulations, synthetic data for health studies.
Vast and transformative applications. Non-stationary online learning is up next, where the data distribution constantly changes.
Like predicting the weather, patterns always shifting. Hard to build an accurate model.
This paper introduces algorithms adapting to these changes by detecting and responding to shifts in data distribution.
Learning on the fly, adapting as the world changes.
Valuable in finance, where markets fluctuate, or robotics, where robots navigate dynamic environments.
AI thriving in the face of change. This next one looks at how deep learning models, particularly layered models like neural networks, discover low-dimensional structures in data.
Deep learning models are often black boxes, difficult to understand. This paper gives insights into their pattern extraction from complex data.
Peeking inside the machine's mind.
Layered models inherently perform regularization through feature learning. By extracting relevant features, they simplify the problem.
Separating signal from noise.
When data has a low-dimensional structure, the model automatically focuses on it, boosting efficiency and interpretability.
More efficient and interpretable deep learning. Models making accurate predictions and explaining why.
Now let's look at a paper on efficient conformal prediction for model ensembles.
Conformal prediction quantifies uncertainty, and ensembles combining multiple models improve accuracy. But combining them is computationally challenging.
Traditional methods can create overly conservative uncertainty estimates, an uninformative safety net.
Balancing accuracy and efficiency.
This paper uses scores from individual models to create efficient, informative prediction regions, like a weighted average of expert opinions, favoring those with a proven track record.
This could be useful in medical diagnosis, financial forecasting, or autonomous driving, where quantifying uncertainty is crucial. Imagine models that provide more precise uncertainty estimates for better decision-making.
Now, our last paper for this part looks at making discrete diffusion models more efficient using distillation.
Diffusion models generate realistic data, but are computationally expensive for high-dimensional data.
This new distillation technique leverages dimensional correlations, the relationships between data elements.
Transferring not just knowledge, but understanding from a large model to a smaller one.
This approach significantly reduces the cost of generating high-quality samples, making these models more accessible and scalable.
Faster, more powerful generative models for image generation, text-to-image synthesis, and even drug discovery.
Imagine creating visual content from text descriptions in seconds, or designing new molecules efficiently. This is the power of efficient AI. It's about making these powerful AI tools more widely available.
What a journey through machine learning research.
Mm.
Game theory, data privacy, the brain, financial markets. AI is advancing on so many fronts.
It's inspiring. Researchers developing new algorithms and tackling fundamental questions about learning, intelligence, and computation.
If you had to choose one key takeaway from all this, what would it be?
The pursuit of robust, reliable, and adaptable AI. It's not just about accuracy and efficiency anymore. Researchers are focused on systems that handle uncertainty, adapt to change, and operate in complex real-world environments.
Moving from specialized AI tools to more versatile and adaptable systems, almost human-like in their ability to learn and reason.
It's an exciting time to be watching this evolution. I can't wait to see the groundbreaking discoveries and applications in the coming years.
And that wraps up our deep dive into the latest machine learning research. We hope you enjoyed it. Until next time, keep learning, keep questioning, and keep pushing the boundaries of what's possible.